Hello everyone, this is part 2 for section 15.3, double integrals in polar coordinates. So last time we went over the theory, we talked about conversion equations, just went over an example to get us kind of warmed up, and we ended up with talking about the theory behind volume. Important thing that we established here was that dA is r dr d theta, so that is extremely important result. And then when we went to our volume formula, we saw how that came into play. So the volume over some region of a function in terms of polar coordinates with respect to the area of that region, again being r dr d theta. And there's your function, the limits of integration, the radial lines, alpha equaling 0, alpha equaling beta, and the functions r1 and r2 of theta. So we're going to need to make sketches to change these regions over to polar coordinates. Basically, polar coordinates are convenient whenever there's an x squared plus y squared, something circular like in the Integrand. That's when we'd like to use polar coordinates, and you can see that's the case here. But we have to consider that basically in the rectangular system, in this case, x is ranging between -1 and 1, and y is going from 0 to the square root of 1 minus x squared. Now, if we consider that upper limit of integration for y, the square root of 1 minus x squared, let's transform that into a standard equation. We'll square both sides. So y squared is 1 minus x squared, and transposing the x squared, we get x squared plus y squared equaling 1, which we identify as a circle with the radius of 1. So basically, what we're dealing with is a circle, but we're only looking for the positive part of this. So that's going to be the top half of a circle. But basically, in the Cartesian system, it's a circle with the radius of 1, but it's the top half. Okay, so that's what it looks like. And x is going from -1 to 1, so it's the whole half a circle, basically. But we want to convert this to polar coordinates, so we consider this is 0, positive x-axis is 0, positive y is pi over 2, negative x-axis would be pi. And if we're taking a little radial strip here, okay, to get this entire region, then when we set up the double integral, well, first off, we also have to consider changing the integrand. So let me say here also, we want to realize that x squared plus y squared to the 3 halves is the same as r squared to the 3 halves, because of course we have the convert from our conversion factors that we stated earlier in the beginning. Always remember r squared is x squared plus y squared. So then that would give us r cubed for the integrand. Oh, and also the formula for the volume. Well, actually, this one's just telling us to use. It's not telling us to plug in to find the volume, so we don't need to state that. But so now we have to set up the double integral in terms of r and theta. And this dy dx, that's our differential dA. And always remember that dA, as we had proven on the previous page, is r dr d theta. So x squared plus y squared to the 3 halves becomes r cubed. and then we have times the r dr d theta. So that's our dy dx, which is equivalent to our differential dA. And now the limits of integration. So with respect to r, this is going from 0, the radius of 0, to the curve. And the curve is given by, so our lower limit is 0. And the curve is just, has the radius of 1. Because if x squared plus y squared is 1, then r squared is 1, and r equals, you can say plus or minus 1. If you know the top half is plus, and the bottom half, well, actually, it would just be equal to 1 because r is always positive. And then it's going to be, so we're going from 0 to 1, and then the limits of integration are from 0 to pi. Okay, so now that we have the integral set up, we can evaluate it, and the evaluation is going to be much easier than it would be if we attempted to do it in fact, this would actually require trigonometric substitution to evaluate this integral in the Cartesian coordinate system. Okay, so before we integrate 0 pi, integral from 0 to 1, let's just make that r to the 4th, dr d theta. Okay, now we can easily integrate r to the 4th. So we have the integral from 0 to pi of r to the 5th over 5, or I'm just going to say 1/5 r to the 5th, and that's evaluated as r goes from 0 to 1. You notice r was what we integrated with respect to, and then that's with respect to theta. And then we have the upper limit goes in, so the integral from 0 to pi of upper limit goes in, so 1/5 times 1, because the upper limit's 1 here, r equaling 1 to the 5th minus lower limit, 1/5 times r, which is now 0 to the 5th. That's with respect to theta now. And so we get integral from 0 to pi of just 1/5 with respect to theta. And you could have pulled the 1/5 out in front of it if you want, but easy enough. That's just 1/5 theta evaluated from 0 to pi. So 1/5 times upper limit pi minus lower limit 1/5 times 0 gives us 1/5 pi. Okay, so the key is drawing the picture and making sure we set up the polar integral correctly. Okay, so another chance here to illustrate the situation. Now, x again is the outer, that's ranging from 0 to 2. Inner limits are with respect to y, so 0, I go from 0 to the square root of 4 minus x squared. Get used to seeing square root of, some number minus x squared or some number minus y squared. That's basically a circle. Let's set it up, show it. Y is 4 minus x squared, so y squared, 4 minus x squared, just like the last example, x squared plus y squared is 4. Okay, but now we're talking about a circle with a radius of 2, and it's still just the top half because y was the positive. But also note that x is only ranging from 0 to 2. So with these vertical strips, let's draw 2 and 2 here, there's no reason to go into the second quadrant, because it's just this part of a circle. Because x, if you went with the vertical strips here, x is only going from 0 to 2. And our, y is ranging from 0 to the graph, which now is r is 2. Because r squared would be 4. So r is, therefore r is 2. And we want, again, this little sweep of an angle. So that's 0, pi over 2. Now that we need it, pi. Okay, so now the double integral. Oh, and then also cosine of x squared plus y squared is just going to be the cosine of r squared, because r squared is equal to x squared plus y squared. Okay, so now this integral becomes the double integral. Okay, we've got the cosine of r squared. Remember, dy dx's are dA, and dA in terms of polar is r dr d theta. Okay, that's the important thing we had proven, and we had restated it up here in the last example. That's the important thing we proved last time. Okay, now the limits. What should the limits be? Well, with respect to r, we're going from 0 to this radius of 2. Okay, so 0 to 2 for r. And then with respect to theta, we're just sweeping through this angle. Okay, so that's from 0 to pi over 2. Okay, now this r can't be multiplied inside, so let me take the time to show this. Integral 0 pi over 2, integral 0 to 2. This would be r cosine of r squared, dr d theta. And that requires a u substitution, but a u substitution where we're just choosing u to be the argument of the cosine, because it's going to fit the cosine of u. The du is 2r dr. Modifying, we get 1/2 du is r dr. And so in terms of the integration, here's cosine of u. The leftovers r dr. That's what makes up 1/2 du. Okay, so therefore we'll bring the 1/2 in front. Have the integral from 0 to pi over 2. Then we call it the integral from a to b. Cosine of u with respect to u. Okay, and then cosine, oops, and my d theta there. There's the d theta. And now integrating at the 1/2, integral 0 pi over 2. Cosine integrates to be sine of u. And that's evaluated from a to b with respect to theta. So that's 1/2 integral 0 pi over 2. But put back our u, which was r squared. So now we have the sine of u, sine of r squared, excuse me. Evaluated as r goes from, because that integration we performed was with respect to r, transformed to u, of course, but with it was going, r was going from 0 to 2. And then all that with respect to theta. Okay, so that gives us 1/2 integral 0 to pi over 2 of, okay, upper limit goes in, so sine of 2 squared minus the lower limit goes in, sine of 0 squared with respect to theta. So that's 1/2 integral 0 to pi. Okay, this is just the sine of 4. It's the sine of 4 radians. Okay? So that sine of 4 is really just a constant. So now, when we integrate this with respect to theta, we get 1/2. I'm going to write theta times the sine of 4, evaluated from 0 to pi over 2. Because I didn't want to write the theta after the 4, because then you might think that it's sine of 4 theta, and it's not. Because sine of 4 just behaves in terms of the integration. The sine of 4, as I had just mentioned, behaves as a constant. So that's just going to tag along in the integration process. And you can pull it out in front if you wanted to. And then you're just integrating with respect to theta, and that's how I got the theta, of course. So this would be 1/2 upper limit goes in, pi over 2, times sine of 4, minus 1/2 lower limit of 0 goes in, times the sine of 4. Second term, obviously, 0. And so it looks like we get pi over 4 times the sine of 4. Okay, so very important part is to be able to set up that integral properly. Alright, so let's see a couple more examples here. This one I left a full sheet of paper for because it's going to be a little bit of a challenge. But let's get started on it. And we're going from x is ranging from 1 to 2. Okay, so the outer is the x again. And that's going from 1 to 2. And I know I wrote 0. I'm going to get rid of that. And y is ranging from 0 to the square root of 2x minus x squared. Okay, so that 2x minus x squared, first off, we can consider that y is equal to, like we did in the previous examples, 2x minus x squared, and then square both sides, we get y squared equals 2x minus x squared. Bring everything to one side, but here, watch what happens. We get x squared minus 2x plus y squared equaling 0. Now we know it's a circle, because we've got a net positive x squared and a positive y squared. But this negative 2x causes us to actually complete the square, to be able to graph this. So x squared minus 2x and something plus y squared equals something. And, I mean, you could say, if you really wanted to here, equals 0 plus something. And that something is what completes the square, which is half the coefficient of the linear term. So half of negative 1 is half of negative 2 is negative 1. And then negative 1 squared is positive 1. So if I add 1 to that side, I have to add 1 over here. And then this can be expressed as x minus 1 is a quantity squared plus y squared equals 1. So this is a circle, but the center is at the point 0, 1, and the radius is equal to 1. Okay, so we're going to be able to sketch the region momentarily. There's even more to it than that. But first off, let's consider that the integrand 1 over x squared plus y squared as a quantity squared can be written as 1 over r squared squared, because x squared plus y squared is r squared, which would be r to the 4th. Okay, and then to be able to realize what the graph is in terms of polar coordinates. Okay, first off, let's make a sketch of it in polar coordinates. So this being r and theta, so 0, pi over 2, pi. I'm not going to need the bottom portion, so you could label it if you wanted, 3 pi over 2. But it's a circle with a center of 0, 1, and a radius of 1. So 1 is the center on either side, 1 unit from 0 to 2. Got a radius of 1 here, so that's going to be a point as well, and that's our circle. Top F, right? Y equals the positive, telling us it's the top half of the circle. Okay, but then one other thing is the fact that in terms of the limits of integration for x, we're going from 1 to 2. So that's x equaling 1 is this vertical line right here. So that's the line x equaling 1. Okay, and we have to know, so if you wanted to make a sketch of the region that we're looking for, okay, we're going for this area in here, because x is ranging from 1 to 2, so in terms of vertical strips, okay, 1 to 2, and y is ranging from 0 to this top of the graph, which we're going to have to find an equation for as well. So with regards to the graphs, in terms of polar coordinates, or maybe I should say the curves, whatever. Let's say the circular piece was y is the square root of 2x minus x squared. So we had y squared equals 2x minus x squared, and x squared, I'm going to say plus y squared minus 2x equaling 0. But then what we're going to do is we're going to use the fact that r squared is x squared plus y squared from our conversions. So remember the conversions on the first page of notes that we went over. This was the conversions that we saw. So we're going to use the r squared equals x squared plus y squared again. We also have to know what x is, and x is our cosine theta. So what we're trying to do is find out what this curve is in terms of r and theta. So using those substitutions, we get that this is r squared, and this is r cosine theta. So now we have r squared minus 2 r cosine theta is 0. If we factor out an r, we're left with r minus 2 cosine theta. Set each factor to 0. R equals 0 is trivial. R minus 2 cosine theta is 0. Gives us r equals 2 cosine theta. And so therefore the graph of this top half of the circle is r equals 2 cosine theta. But then also we need to know the graph of x equaling 1. So for x equaling 1, we have, again, r cosine theta, because we need in terms of r and theta, and x is r cosine theta is 1. Solve that for r, you get 1 over cosine theta, which is secant of theta. And so that graph is r equaling secant theta. So now when we go to set up the integral, we have the integral from, okay, it's the double integral now of 1 over r to the 4th. So remember, we had converted the integrand to r to the 4th. The dy dx, again, is the dA, and this is where dA is r dr d theta again. So we get an r, we get the 1 over r to the 4th times r dr d theta. The limits of integration with respect to r, the radius, is we sweep through this. If we took these little differential d theta sweeps, we're going from this part of the curve, which is r equaling secant of theta, so that would be the lower limit of integration, to this part, to the circular part of the curve, which is 2 cosine theta. And then the angle is ranging from 0 to this point right here. Okay, would be what it's sweeping through. So it's picking up little pieces here, but it stops right here at that point. At that point, that's the radial line. So the lower radial line is 0, but the upper radial line, well, if this value of x is 1 and this value of y is 1, then that must be a 45-degree angle. So this value that we'll call beta, because that's the upper limit of integration, would have to be pi over 4. And so there's pi over 4. Okay, so quite a complicated setup. I'm going to stop right there. We'll come back, we'll recap this, and finish it off in the next part.